in the addition of a Bronsted acid across a double bond, the proton can bond to one of two possible carbon atoms. In each reaction that we've looked at so far, the alkene has been symmetric so that the same adduct is produced regardless of which alkene carbon gained the proton. So of course, the burning question in your heart, I'm sure, is what happens when it's not symmetric? With an unsymmetric alkene, like we see here with propene, you end up with two constitutional isomers. So we have two constitutional isomers. And you can see for here, there's one chloropropane and then there's two chloropropane. In this case, 2-chloropropane is the major product. And so the question that we always ask ourselves in science is why? Why is 2-chloropropane the major product and 1-chloropropane is the minor product? What makes it so that 2-chloropropane is major? Okay, well, to answer that question, we look at the free energy diagram. So remember from the previous screencast that the overall product of an electrophilic addition reaction is going to be significantly more stable than the overall reactants. Okay, so the products here, boom, are more stable than the reactants. Electrophilic addition reactions tend to be irreversible and generally take place under kinetic control. So electrophilic addition reactions tend to be irreversible and generally take place under kinetic control. As with any kinetically controlled set of competing reactions, the major product is the one that's produced the fastest, right? So the major product is the one that's produced the fastest. Because the first step of the mechanism right here, which is the formation of the carbocation intermediate, is the rate determining step of the overall reaction, the major product comes from the carbocation intermediate that's produced the most rapidly. So the major product comes from the carbocation intermediate that is produced the most rapidly. With this in mind, if we look at this figure, which is 12.5, it shows the free energy diagram for the formation of 1-chloropropane, which is the red line here, okay? And it shows the formation of 2-chloropropane, which is the major product, and the blue line here. The carbocation intermediate that's produced by the addition of that proton to the first carbon, which forms here to C1, right? This guy is a secondary carbocation, so it's more stable. This is a primary carbocation, so it is less stable. Because the two carbocations are produced from the same type of elementary step, production of this second carbocation involves a smaller energy barrier and is faster. And so the second carbocation leads to the major product, which is consistent with what we observe in the laboratory and what we talked about in equation 12.6 on the previous slide. Now, we can generalize this kind of idea in as kind of follows here, which is the major product of electrophilic addition of a Bronsted acid to an alkene is the one that proceeds through the most stable carbocation intermediate. And you need to remember here that tertiary is more stable than secondary, which is more stable than primary. Okay, so this is where that information is applied. Now, if we continue to look at this a little bit, there's some pretty easy ways to predict it. When we look at this reaction here, so what's going on is HBr is added to 1-methylcyclohexane, and we end up with a major product that's 1-bromo-1-methylcyclohexane. That's a 75% yield there. When we look at the intermediate for this reaction, right, we can see that you can form a carbocation here, that intermediate, which is tertiary, or, which of course then leads to that. You can form a carbocation here, which is secondary, but that would go through a rearrangement to form a tertiary carbocation. So, tertiary carbocations are more stable than secondary carbocations, which are more stable than primary carbocations. Now, before the mechanism for the electrophilic addition was known, the Russian chemist, which is shown here, his name is Vladimir Markovnikov, and he lived from 1838 to 1904, and he made the following generalization to describe the reaction's regioselectivity. And I've got that written down here for you. The addition of a hydrogen halide to an alkene favors the product in which the proton adds the alkene carbon that's initially bonded to the greatest number of hydrogen atoms. Now, I have a very active imagination. It's one of the reasons why I love chemistry, because you get to make up all sorts of stories and it's super fun. And so this is how I kind of think about it. I kind of think about this proton. This proton, he's real social. He's one of those real social people, and he's going to go to the party with the most protons, okay? When we look here, this carbon has 4 bonds to it. There's no hydrogens there, right? There's no protons, there's no hydrogens. When you come over here, this carbon has 1 hydrogen. So this hydrogen can go party with that hydrogen and form CH2. That's how Sarah Pierce would have written the rule, because everybody loves a good party, but not how Russian chemists wrote the rule in the mid-1800s. So we now know that Markovnikov's generalization is just the outcome of the reaction favoring the more stable carbocation intermediate. However, his generalization has come to be known as Markovnikov's rule. And I will refer to this rule a lot, all scientists do. And the type of regioselectivity it describes is called the Markovnikov addition. And so this is a common addition that you'll see. So let's do an example. Predict the major product when endene, which is shown right there, is treated with hydrochloric acid. Endene has lots of double bonds, right? And we're going to treat it with hydrochloric acid, and we know this is going to be an electrophilic addition reaction. So the very first thing you need to decide here, because there's lots of double bonds, is which carbon-carbon double bond will undergo the electrophilic addition. Well, we previously talked about the fact that these guys here are part of benzene, and they are part of an aromatic ring, and it's too unfavorable to break up the aromaticity. So that's not going to happen, okay? So red, stoplight, that's not going to happen. Here, I'm using green, kind of to show you as go. That's the one that's going to react. There's also an arrow to it right there, okay? So the other double bonds are not going to react because they are part of an aromatic ring, okay? So that's the one that's going to react. So we've answered that. We just did it above with that, with the image itself. Now, the next question you need to ask yourself is, what are the possible products and the corresponding carbocation intermediates for which they are produced? When we look at this, at first blush, there are no difference in hydrogens there, right? On that carbon, on each side of the double bond, both of those have one hydrogen. So there's no difference there. So we have to look and say, is there anything else that can affect the stability of a carbocation intermediate? So I'm going to come down here and look at the mechanism. So I'm going to draw my benzene ring here. Put my double bond there, right? And I'm going to add HCl. I know that the double bond that's there has a lot of electron density. We talked about the reasons why in the previous screencast. And so I know that is electron rich. I come over here, I look at the chlorine, that's super electronegative. It's going to withdraw electrons. That makes that proton partially positive. We know negatives and positives like each other. So this is a lot of electron density. It's going to come out. It's going to steal that proton. Those electrons are going to go on the chlorine. It can form one of two intermediates. It can either form this intermediate, all right, or, and is really what we want there, not or, so let me get rid of that. And it can form that intermediate, okay? Now, there is no difference in the number of hydrogens. And so both of these would be secondary carbocations. But we have to ask ourselves, is there anything else that can help stabilize one of these over the other? And there is. If we look at this guy right here, and I should have, we're using analogies of red and green, so I should have done this in green, because that's the one that's going to go. If we look at this guy right here, that is a benzylic carbocation, and so it's resonance stabled. So that guy there is a benzylic carbocation and is resonance stabilized. So it's more likely, it's going to have lower energy, and since this is kinetically driven, it's going to form faster. And so the chlorine is going to come in and attack that carbocation intermediate. And the major product that's going to form is going to be that guy right there, right? So that's our major product. A lot of times you need to watch questions, particularly on tests, because the question is going to say, what is the major product that is formed? Okay, and you need to identify the major product. So we can use Markovnikov's rules, but really it comes down to which carbocation is the most stable. Now, one of the things that you have to watch out for here are carbocation rearrangements. So I want you to notice that when 3-methyl-butanone is treated with hydrochloric acid, you get fairly significant amounts, kind of equal parts, 2-chloro-3-methylbutane and 2-chloro-2-methylbutane, right? Both of these are produced. 2-chloro-3-methylbutane is the product of a normal Markovnikov addition to HCl across the carbon-carbon double bond. Specifically, it's going to add that proton to the first carbon of the alkene, and chlorine adds to the adjacent on the secondary carbon. On the other hand, 2-chloro-2-methylbutane, the chlorine appears to have attached to a carbon that was not initially part of the double bond, okay? And so what we end up here with is any mechanism that proceeds through a carbocation intermediate can have a carbocation rearrangement. So this second guy here is the product of a carbocation rearrangement. So anytime you can have a carbocation, in a mechanism, you must double check that you are not going to have a carbocation rearrangement. Now, we've talked about that mechanism before, but I just want to review. So let's look at the carbocation rearrangement mechanism. So this, and I'm going to use the previous example. And so we've got HCl here. The double bond is very electron rich. It's going to come and attack the proton because that's partially positive. Those electrons are going to go on the chlorine. It's going to pull the proton back, right? And what's going to happen is it's going to form that carbocation. Okay, that's the main carbocation it forms. This has 2 hydrogens. This only has 1. Hydrogen's going to go party with all its friends here. That leaves us the carbocation there. Now, I want you to notice this carbon has 1, 2, 3 R groups, but it also has a friendly proton on it, which I'm actually going to draw right there. Okay, so there are 2 R groups and a proton. And so this can go through a 1,2 hydride shift. And I left out over here, I said it, but I didn't write it. I want you to write it. It's the electrophilic addition. So it goes through a 1,2 hydride shift where this hydride shifts over there. When that hydride shifts over there, we now end up with a tertiary carbocation. And the chlorine comes and attacks that tertiary carbocation through a coordination step. And there we go. That's our product. So there's 2-chloro-2-methylbutane. So we just end up with a hydride shift before the coordination step. Hydride shifts are really fast, and so that's what happens there. So let's do a problem. So we're going to draw the complete detailed mechanism and predict the major product for the reaction shown here. Now, if you want to try to work this, you are more than welcome to pause and try to work through this and then restart. So if you want to do that, go ahead and pause me and then restart. But I'm also going to work through this as well. So we're looking at this. We see there's a double bond. There is a strong acid. So that indicates to us, hey, we're going to go through an electrophilic addition reaction. And so now I need to think about what products am I really going to get. Okay. And so the first question I need to ask myself when I'm drawing this mechanism is, and that's partially, sorry, I got that backwards. That's partially negative, right? Super electronegative, that's partially positive. So I know, right, that these electrons are going to go out and attack that proton, and those electrons are going to go on the bromine. Now, the question is, where is that hydrogen going to go? Well, when that hydrogen goes back, right, that proton goes back, there are 2 protons here and there's 1 proton there, okay? So it's going to go here and form that carbocation. So the proton has gone on this carbon here and it's formed the carbocation there. Now, we understand the reason it does that is because that's a secondary carbocation. And if the hydrogen were to go there, here would be a primary carbocation. Secondary carbocations are more stable. So that's super duper stable. Now, at this stage, you need to stop and look at the second question. And you always want to ask yourself the second question. Can the secondary carbocation intermediate undergo a 1,2 hydride shift or a 1,2 methyl shift to attain a greater stability? Okay. In this case, we look to this side because if one of these hydrogens were to shift here, you'd end up with a primary carbocation, and that's less stable. So let's look here. We don't have any hydrogens on this sucker here, but what we do have is a methyl group. And that methyl group can shift right on over to that carbon right there. And when it shifts to that carbon right there, we end up with a tertiary carbocation, and that's more stable than a secondary carbocation, right? And so that would be our carbocation. So this first step is electrophilic addition. And the second step is a 1,2 methyl shift. So you've seen a hydride shift and you've seen a methyl shift here, right? So we see that methyl shift. Then what's going to happen is the coordination step. So we have bromine minus that's running around. Those electrons are going to come here. They're going to attack that carbon. They're going to form a new bond through a coordination step. And that's now our product. So we've solved this problem. We have predicted the major product here. Now, practice is going to be the best way to really, so make sure you practice it quite a bit. All right, in an electrophilic addition reaction involving an alkene, both alkene carbons, which are initially planar, okay, which we see here, become tetrahedral in the product. And so it's possible for new chiral centers to be produced during the course of the reaction. And whenever we get new chiral centers, we have to talk about stereochemistry. So, for example, in the reaction shown here, we form a new chiral center. And so because of that, we're going to form a racemic mixture of products. So we're going to end up with 2 products here because we make a new chiral center. So if a single chiral center is formed, then you end up with a racemic mixture. So that, remember, is achiral. Now, just as an interesting aside, this 1,2-diphenylethene, which is also called stilbene, provides a framework for really several useful derivatives. And one derivative is used as an optical brightener in laundry detergents. And so that gets your whites whiter. Okay, that's one of the derivatives. But it also has, some of those derivatives have the ability, they're researching them for cancer fighting drugs. So that's kind of an interesting aside there. If you have 2 chiral centers that are produced, here and here, 4 stereoisomers can exist in the product, okay? You can have RR, RS, SR, and SS. You can see the mechanism here, right? In the first step, that electrophilic addition, you can have both R and S being produced. And then the second step, where the bromine comes in here, you can also have both R and S being produced as well. So anytime we form a new chiral center, we are going to end up with kind of this racemic mixture.